Today's chapter is Form 4, Chapter 3, Gravitation. Gravitation is about Earth, about Sun, about Kepler's law, Newton's law, satellite, and all those things. That's above the Earth. For step number 1, let's start with step number 1. What time do we start now? 8:10. Start. So we created 4 drawers. And these 4 drawers are Newton gravity, Kepler's law, man-made satellite, escape velocity. As usual, we will create a story that can help us to remember these 4 drawers easier. And I created a very short story. There's a guy called Newton. Maybe it's your friend, or maybe you can imagine the scientist, the very famous scientist, Isaac Newton. He stapled the satellite. Staple 是你知道那个我们不是有 staple 纸的我们每次讲staple 起来 staple 起来就是那个 staple 是吗？这个 Newton 呢，他就 staple 那个 satellite 是一个很大的东西嘛，他就拿一个很大的 staple 就 staple 它，就是去钉它啦 ，OK， 然后satellite try to escape， 很明显satellite 一定要跑嘛，因为 staple 到它会痛嘛，是吧
Okay, I think actually we did this before. Actually,
did we?
I feel like we did. There's I remember the Ong Apiang and the man-made satellites. I think I remember the centipede.
Okay. Okay, so shall we continue? As a revision? Okay, let's do a revision. So, but this story is new. I did not create this story last time.
Okay.
Right. So this is helping us to remember the 4 drawers. So Newton, staple sounds like a bit like Kepler. Satellite is the man-made satellite. Then the satellite tried to escape. So the satellite tried to escape. So there's escape velocity at the top drawer. So in total, we have 4 drawers. So that is step number 1. Then step number 2 is reading the keynotes. So as you can see, there are so many formulas. So for now, we just try to read the formula. And if you do not understand fully, it's fine. Let's take maybe 3 to 4 minutes to read this. Once you finish drawer number 3, then you tell me, I'll scroll down. Let's start now.
Yeah.
Done. Okay, let's scroll down a bit more. Okay, here.
Okay.
Okay. Now, okay, let's read the summary one by one, each drawer. Then once you finish the drawer, I will explain the small story for that particular drawer. Let's move this away. So now we go into step 3. And step 3 is on the left, and step 2 is on the right. So you can take it as a reference. So we can start now.
Okay.
Okay, until here.
No.
Okay.
Okay.
Okay, there are two key points over here. The first key point is talking about the force, right? The gravitational force, F equivalent, the F. And the gravitational force is related to two bodies. And these two bodies we are talking about is not the human bodies. It's talking about the two planets. Something very, very big, extremely big, like Earth or Sun or Mercury or Venus or Jupiter. That's the first point. The second point here is talking about the distance. So the gravitational force is being based on the formula is the factor of the mass of the two bodies, or which is the two planets, and the distance. So you have this r square, right? So it's influenced by the mass and influenced by the distance. When the mass is big, and then the force is going to be bigger, right? Because if you look at the formula over here, this is nominator, this is denominator. If you want the F to be big, your nominator need to be big. If you want the F to be small, the denominator needs to be small. So the denominator is the distance between, let's say, the Earth and the Sun. And the M1 is the mass of the Earth, and the M2 is the mass of the Sun, if you are calculating the gravitational force between the Earth and the Sun. So what happens if there is another planet like a Sun, exactly like a Sun, and if it is nearer to Earth, so the force is going to be, the gravitational force is going to be much higher, right? It's going to be much higher because you see the distance is r squared, right? So the distance is going to be r squared. So the further you go, the faster the F is going to be reduced. So it's not like a linear because this is not r, this is r squared. 越那个 distance 呢会影响那个 force 越大的 force 越大的 distance 呢会影响那个 force 更快会 decrease 那个 force. Okay, so that is the point number one. Right, let's continue on this.
Okay.
Okay, 这个就是 derive from 上面的 formula 是吧？你看啊，上面 formula 其实就是这个啦，没有看 F 等于 G M1 M2 除 R square。如果你看这个的话，它的 F 其实就是 mg，然后 G M1 M2 除 R square 一样的东西。不过这个是上面那个是一个 general 的 formula，这个是 for gravitational acceleration，就是 Earth 的，就是算 Earth 的，因为 Mercury 的 gravitational acceleration 又不一样，然后 Venus 的也不一样 ，Jupiter 的也不一样。这个1.2呢是单单就是 focus on Earth 的，所以算到来是算到这个什么9.8亿的 ，OK？你看它就是看 Earth 嘛，你看 Earth 的那个重量是这个嘛，很重很重嘛，我才70 kg，你可能才30 kg 啊，是吧？这样你看这个是5.97乘10 quasar 24 kg 是超级无敌重的，是吗？这样它有拿它的 radius 就是 Earth 的9加力咯，Earth 的那个 radius， 然后它就可以算出来啊，它就可以算出来。好，来开始涂这个。
嗯，OK，
OK，这个下面会有再讲啦，这个其实暂时不是很重要，等一下你读一下你就明白了。
OK，
OK，它的 formula 很吓人哦，这样的 OK，所以不要担心，这个其实 Kepler law、Kepler third law 会讲到，所以这1.3跟1.4都先不用这样担心，如果你不明白。好，我们已经完了 Chapter F，Draw One，Draw One 呢就是这几个 keynotes 啊，其实讲的东西就跟刚才我们讲的东西就是差不多，有点大同小异啊。就是第一个是 the first one is direct proportionality mass to mass and inverse proportionality to square of distance. So this is talking about direct proportionality to the mass, which is the bigger the mass is, the bigger the force. Then inverse proportionality to square of distance, which is the bigger the distance, the smaller the force. So F is what force? Gravitational force. And G is a gravitational constant. Okay, it's a constant. So just remember that. Then gravitational acceleration. This is 9.8. This one I think we know. And this is how we calculate the gravitational accelerations. G is the constant. M is the mass of the Earth, the 5 point something times 10 to the power of 24.
yeah,
Yeah. Then this R is the radius of the Earth. Now, this is something interesting. Gravity, I'll read it out. Gravity is 0 at the center, increases until you reach the surface, and then decreases with distance outside the Earth. So, if imagine you are at the center of the Earth. At the center of the Earth means you are at the center, which is you go from where you are now and you walk 6.737 to the power of 10 to the power of 6 meter, and you dig the ground into the center of the Earth. Right? The gravity at that point is 0. Why? Because the R is near to 0. The gravity at the point is near to 0, and the R is near to 0. Okay? And if you increase and you go out from the center of the Earth and you reach the surface, and then this is your gravity. This is your gravity. Okay?
okay,
Then it will decrease when the distance is outside the Earth. So if you are 40 or 50 kg down, and if you stand at the near to the Earth center, then you are lesser. Your weight is not 40 to let's say 45 kg. Your weight is not 45 kg anymore. And if you travel outside the Earth's surface, and also you can be lesser than what you are now. Okay.
okay.
All right. Now let's create the story. Earth and Sun married. OK， 地球跟太阳结婚了为什么结婚呢？其实就是讲，其实这个gravitational force 就是在讲两个很大的东西，就是很大 the big mass of two celestial body. They are having a gravitational force between them, right? Then Shy Gavin keep a distance 9.8 meter, but if it is too far, then his heart will be broken. Right? Gavin is having with girlfriend. Gavin is having a girlfriend, and his girlfriend, he's very shy. If his girlfriend is too near to him, he's shy. But if the girlfriend is 9.8 meter away from him, then this is a perfect distance. But if the girlfriend is away from him more than 9.8 meter, then his heart is broken. Right, his heart is broken. This is to explain this one. Right, this is to explain this one. But the most important story is this one. Earth and Sun marry. Because this is talking about the gravitational force between two celestial bodies. All right?
Okay.
Why did I add this? Because I thought this is interesting. Okay. Now, next, let's go to drawer number 2. Okay, let's read drawer number 2 from here to second law, until second law.
Okay.
You read the third law first, then we'll explain the story.
All right.
Okay. So 这个呢就是 Ong Ah Piang. Ong Ah Piang is what? Ong Ah Piang is a guy that has many girlfriends, and the nearer the girlfriend to him, his heart beat faster. And the KL girlfriend, he meet more frequent. For the girlfriend living in US, he meet less frequent. So how do I explain this? So Ong Ah Piang is orbit, area, period. Right. Orbit means, if you read here, all planets move in elliptical orbits with the sun at one focus. So sun is like the Ong Ah Piang, which is having many girlfriends surrounding him and many planets surrounding him. You have Earth, you have Jupiter, you have Mars, you have Venus, and so on. So this is to explain, Ong Ah Piang has many girlfriends, is to explain the Kepler's first law. There is planet that is moving, planets S with the S, which is moving elliptical orbit with the sun in one focus, right? And number one is there are many planets, and number two, why it called orbit? Because they are not moving in a circular shape. It's an orbit. Orbit 跟 circular 你知道它的区别吗？
orbit 跟
orbit 就是它不是完全是圆形，它不是完全是圆，它有一点
it's more like
oval
ovalish.
oval 这样的，对，这个就是 orbit 了那个就是 orbit。所以这个 Kepler's first law 就是讲这些 planet 是围绕在这个太阳是用 orbit 的这种形状去围绕的，不是圆形。OK，number two 就是 area 就是阿扁嘛，R 嘛，阿扁，阿扁是 period sorry，R，这样 R 是什么呢？Nearer and faster speed。他要讲的意思是什么呢？就是你看orbit 就代表它的那个distance from 那个 planet 跟 sun 是不一样的嘛，因为是 orbit。如果是 circular 的话，就是每一个点都是一样的，它的 distance between sun 跟let's say earth，对吗？orbit 就是不一样，不一样的话是怎样呢？它越靠近那个 sun，它的那个 speed 就会越快你明白吗？它越远 from 那个 sun，它的 speed 就会越慢这个就是说，when the girlfriend is nearer to Ong Ah Piang，Ong Ah Piang heartbeat will beat faster beat faster 就是更快咯，或者是 girlfriend 的 heartbeat will beat faster 啦，因为其实是 planet 在跑嘛，不是 sun 在跑啊这样也是可以。这样它这个意思是什么呢？为什么它会 sweep out equal area in equal time？你想一下，如果你现在很靠近你的那个山，你的那个 area that you cover is smaller when you are away from the sun，对吧？这样如果你要 equal area 的话，有什么东西要变呢？就是你的 speed 要变哦。你的 speed 要变，你的 speed，你靠近那个山，你就跑很快，跑比较快过你 away from 那个山。right？ So 边那个边是 period that's why OK， 先讲讲回R 就是 area 咯，其实它就 focus on 那个 area 嘛，那 area that is equal 你那 area that is cover 是 equal 的，although 你是一个 orbit。然后边呢就是那个 period 咯period 是什么意思呢？就是讲他 on 边 meet KL girlfriend more frequent than meet US girlfriend，right？Because orbital period 是一圈，Earth 跑一圈是365天。如果是 Jupiter 应该是后面的后面那些的比较远的，这样它跑一圈一定是超过365天的嘛。然后前面的那些什么 Mars 什么东西比较前面，忘记前面是谁了他跑一圈一定是比较快过365天这样这个就是 讲 orbital period， 就讲on 那边 meet the nearer girlfriend more frequent than the girlfriend that is not
further
near
away
to
的。
him. Yeah, further away.
Okay.
Right? And what is the relationship? The relationship with 这个 orbital period 什么呢？T square proportional to R cos 第一个。OK，因为我们现在讲越远的 planet 呢，它的那个 orbital period 就会越大嘛。不过它不是一对一它不是你一 increase 1个 kilometer，它就 increase 1分钟或者1个小时，不是这样。它的 relationship 是 cluster dual 跟 cluster 第一个的 relationship。OK，好，这样这个讲完了咯。这个故事应该很清楚。Right, so let's go to drawer number 3. Let's do this.
Okay.
Okay, let's do this.
Okay.
OK，这个比较简单。这个的 story 是 Geoffrey spin centipede，有一个小弟弟叫 Geoffrey，他 spin 那个 centipede。这个就是 spin 那个 centipede，这个 centipede 其实就是centrifugal force，centripetal force，centripetal force。centripetal force 其实就是我们刚才所读的 gravitational force 来的。你想一下那个 satellite，为什么它可以在空中上面不会掉下来，也不会飞掉呢？就想象 Jeffrey 或者是你绑绑一个rock 啦，或者一个球，你在那边晃，在那边晃一个圈圈这样晃。为什么那个圈圈为什么那个球不会飞掉呢？因为有一条线呢，有一条线绑住它，对吗？那条线呢，其实就是如果你用 satellite 跟 Earth 的解释的话，为什么那个 satellite 不会飞掉呢？就是因为那条线就是 gravitational force， 看不到的，不过就是有一个 force 这个就是 Drawer One 讲的东西。他先开始就跟你 introduce what is gravitational force， 两个物体，两个 celestial body， 它们是有一个 gravitational force between each other 的。OK， 这样这个就讲完了。这个 Jeffrey 就是讲那个 Geo satellite 咯，然后 spin centipede 就是那个 centripetal
centripetal force。
是这样的意思。OK，
好的
the last one will be very easy.
escape velocity。OK。
Escape velocity, what does it mean? Okay, let's go back to the same example, the satellite. Why satellite can be orbiting the Earth and it's not flying away into the universe, into the galaxy, is because, like we mentioned just now, there is gravitational force between the satellite and also the Earth. Now, let's take back the same example where you or Jeffrey spin the centipede. So there are actually two forces. One force is the force of the string that is connecting from your hand to the centipede body, right? And that is what we call gravitational force. And there's another force that is moving the centipede around the circle, right? Around the circle. So that is two forces that need to be available to make this satellite to be spinning around the Earth. Imagine if the velocity of that centipede or that rock is much faster, so fast that it is going to be breaking the string that's holding between your hand and also the centipede, right? And that's what we call escape velocity, right? So the story that I created is rocket goes up, then turn right at 7.7 kilometer. He will not escape. He will still be in the orbit. But if it is more than 11.2 kilometer per second, then the rocket will escape out from the Earth orbit. Then you will be in the galaxy and forever he will not be able to come back. Okay? Right? So let's recap a bit. What are the four drawers?
Shy Gavin, the Ong Apiang, the centipede and Joffrey spinning it, and there's also the rocket. For
Right.
Shy Gavin, it's like if Gavin gets too close with his girlfriend, then he'll be like shy. 9.81 is like the perfect one, and if it's like too far away, then he have heartbreak. Ong Ah Piang is like he has lots of girlfriend, and like he's like closer with the ones like that are closer to him, and not as close with the ones like are further away. Man-made satellite is Joffrey, which stands for like geostationary satellite, spinning the centipede. The centipede is the centripetal force. And escape velocity is like as the rocket goes up, it turns right at like 7.7 km per second, then it's like not going to get out.
You missed the heartbeat. Do you miss the
Oh
heartbeat?
yeah.
Yes.
Ong Ah Piang.
Okay. Yes. Heartbeat is the Kepler's law number 2. Okay. Shy Gavin keep a distance, and if it is too far, the heart will be broken. This also explain the relationship between F and also the distance. Right? Okay, that's good. Let's go to step number 4. Okay, let's start from here. Drawer 1. Okay, let's read.
Okay.
Okay, I hope by now this formula doesn't look so scary anymore.
Yeah.
Right, now you understand. Okay, and this is the gravitational force constant. Unfortunately, this is something you need to memorize. I think they will give you, right, during the exam, they will give you these numbers, some constant.
Yeah, at
Today?
the front they will.
Yeah. Okay. Number 2, drawer number 1, this is drawer number.
Okay.
Okay, this one is talking about combining the Newton's second law and also the Newton universal law. Right. So if you see the M, what is this M? This M actually is the mass of the satellite. So we are talking about the satellite and also the Earth. So when you put these two formulas together, then you cancel out the M, the small m. The small m is the small m is the satellite mass. So what does it mean? It means that the mass of the satellite has no it's not a
It's
factor
not
of
affected.
it's not a factor. It's not affecting the gravitational force. Right? No matter how heavy is your satellite or how light your satellite, the gravitational force is still 9.81.
It doesn't affect it.
Yep, you're right. Okay, let's go to drawer number 2.
Okay.
Okay, this is exactly Ong Ah Piang's story.
Yeah.
All right.
When the
Okay, let's
girlfriend reaches the orbit nearer, faster heartbeat the area, and then like more frequent for KL. That one's the period. All right.
Okay, it's easy now. Let's go to number
Oh.
4. Still drawer number 2.
Mm. Faster when closer to the sun. Okay.
Right. Okay. So now drawer 2, this 1, 2, 3 law, Kepler's law doesn't sound so scary anymore, right?
Yeah.
Okay, good. Drawer number 3.
Satellite. Mhm. Okay.
Okay. This is the Joffrey spinning the centipede.
Yeah. Okay.
Okay. Drawer 4, question 7.
All right.
This formula you have to memorize, okay?
Mm.
Or maybe it's given in your first page of your exam. But if you're interested to know how this formula is being derived, it is from here. It's actually also taking from the gravitational force and also the Newton's second law. Then that's
Oh.
how you get this, right?
Okay.
Okay. But when you have more time, then you can go into this detail. Let's go to the last one.
Containing atmosphere, space exploration. Oh, there's one more. Okay.
Okay. Now, let's do a quick recap. The Newton stapled the satellite, and the satellite tried to escape,
Mm.
right? And that is the 4 drawers. And yep, let's try to go to the guide. Okay, let's do it. This is drawer number 1.
I get win one.
Yeah, you have to intentionally identify if there is new information or new knowledge.
Mm. Mm. Okay.
Okay, I think there's not much new information. It's talking about uh, the two, what do you call it? The 2 points, which is directly proportional to the mass and also inversely proportional to the
So
square of the distance. Yeah.
yeah.
Okay, and this part here.
Okay.
Okay, drawer 2, Ong Apiang.
On Apiang has many girlfriends.
Yep.
The 3 laws. Okay.
Okay. This a little bit more.
Hmm. Okay.
Okay, drawer number 3 now.
Your face spinning the centipede.
Yep.
Okay.
Okay，我不知道你明白这个吗？Free fall around the earth，明白
Before
吗？
was like from another chapter, right?
No, this is this
No?
chapter. This
Oh,
chapter. Okay, what does it mean
gravity.
by free fall around the world？它其实就是你这个 satellite，你还记得我们不是有讲一个escape velocity 吗？
Uh-uh.
就是这个是它有一个 velocity，就是 horizontal 的一个 speed。horizontal speed 就是它有一个 perpendicular 的 speed，就是那个 gravitational force 嘛。然后 horizontal 的 speed就是我们讲这个velocity。这 velocity 呢，你想象，如果你现在丢一粒球啊，你现在站起来，你丢一粒球啊，那个球会直飞，然后它会慢慢 projection 这样跟着那 projectile 会这样掉下来嘛？为什么它会掉下来呢？是因为它有 gravitational force 去拉你下来，对吗？你想一下，你现在再丢大力一点你丢大力一点，它就会飞更远，然后才去更远的地方掉下来。这样你想象，如果你再丢更大力，会不会更远更远才掉下来？这样你想象，如果你是可以丢到快到什么程度呢？快到你要，因为我们的那个地球不是直的，我们的地球是圆的嘛，对吧？这样如果你可以丢到快到它是在那个地球的那个 surface 一直在那边转，它一直在那边转，这样它就永远就不会掉下来了。你没有讲过吗？
呀，一直还在那边动，还在找。
因为它一直好像要掉下来的时候你就已经你的地球已经 curve 过去了。这样它没有掉下来的时候，你就已经 curve 下去了，所以它就一直很像他讲，一直好像 free fall around the earth 咯。它一直要掉下来，不过掉不到，因为那 earth 是圆的，earth 不是直的，不是平的，对吧？这个是它这样的意思所以它就有一个7.7 kilometer per second。如果你可以丢到这么快7.7 kilometer per second 这样那粒球就永远不会掉下来。不过呢，这个7.7 kilometer per second 呢，是在我们现在在这个地球的这个Earth surface 是不能实现的。为什么呢？是因为我们这个地球的这个 Earth 呢，它是有 friction，就是说我们讲那 atmospheric，就是有 particle of oxygen 啊，carbon dioxide 啊，有很多 friction 啊，就
嗯
变成你那个球，你不管你怎么样丢都好哦，你可以丢到7.7 kilometer per second，不过你 after a while，它会 decrease in speed。为什么它会 decrease in speed 呢？因为有 friction 嘛，friction dengan 那粒球还有那个udara，还有那air，这样
有 resistance。
你就会少了那个 energy，kinetic energy 会少，所以你这7.7是你是维持不到的，缅甸不到的为什么 satellite 可以做到呢？因为它不是在
地
Earth
球。
surface Earth，它是在天空上，然后在那个 space 上面嘛，space 上面是没有是 vacuum 来的，对吗？vacuum 就没有 udara，没有 gas，这样它就不会有 friction of 那些udara or gas that is slowing down 它的 speed，所以它的 speed 就会 maintain 7.7 kilometer per second，这样的话它就会永远 falling down around the earth 明白
明白。
吗？OK。因为很多时候呢，人家误导，以为我们这个 satellite 是没有 gravity，所以它才不会掉下来。因为 gravity 一直拉一直拉，你会掉下来吗？那个 satellite 是有 gravity 的，不然 satellite 它为什么不掉下来呢？因为它有这个velocity 就是7.7，不是 escape velocity，escape velocity 它就飞掉了。它还有一个 velocity 这个 velocity 呢是可以维持它一直在那边 fall around the earth，因为 at the same time 我们又有 gravitational force 去拉下来，所以它一直在那个地球的那个 curvature 那边一直在那边掉，一直掉，不过掉不下来。I hope this is clear。
可以，谢
OK，
谢。
好，这边读了没有？还没有读应该
到一半。
啊。
OK。
好，last drawer。
OK。
OK，完了。OK，
Nice。
quiz 我们就 is the same type what is this? Okay, so you read the questions and tell yourself which drawer, and then from this drawer take some keywords to form the answer before you read the answer. Okay, let's do it.
Gravitation. Yeah. Sine heaven. What is the GM1 and 2 over distance of two bodies thing? Okay. It says that. What is that? Alright. Two factors determine magnitude ratio between two bodies. Their relationship to the force. Force two bodies distance, right? Yeah, don't forget that. distance from the thing force proportional to mass, pretty sure. And then if it's a larger mass, larger force. Smaller mass, smaller force. Force is let's get distance. Also the formula. Alright.
Okay, first question and second question is almost the same, but just different way of asking. Okay, let's go to third question.
Centrifugal force. Oh, centrifugal force is the third drawer.
Yep.
Satellite orbiting the Earth. Geostationary satellite. Centrifugal force spin 24-hour. Sure. Gravitational pull. Yeah, okay. So it's stable orbit around Earth. Gravitational force necessary centrifugal force. Alright.
Okay.
Oh, this one is the second drawer. This one is Apyeong has many girlfriends. The orbit of always is like faster when it's closer to the sun. Yeah, faster when it's closer to the sun, slower when it's further away from the sun. Distance is not constant. Yeah. Okay.
Okay. First law is just talking about orbit, right? The second law is talking about the speed. They're
Nearer
covering the
equals
area.
faster heartbeat. Yeah.
Yeah, they cover the area.
Second is the law of areas. Changes when it's so yeah. Faster when closer to the sun, slower when it's further from the sun. Move faster. Oh yeah, okay. Equal areas, equal intervals of time, larger arch areas, same time near the sun. Alright.
Okay, let's go to 6.
Oh, fourth drawer. The rocket drawer. The rocket goes up, it turns right, 7.7 kms. This is the factors that determine its value. It says M. It goes up, turns right, so that's the distance. It's nothing to do with mass, I'm pretty sure. Yeah. Okay. Minimum velocity of an object on the surface of a body of
等一下，这个 number 6其实就是在讲这个 formula 就是这样吧。
okay.
terangkan 这个 formula 就对了。他其实讲的东西也是讲这 formula。
Okay. So it's the formula in words. Okay. G and G. This one's the first drawer, is it?
Yeah.
Between the acceleration of the planet and the universal gravity. So this one's the formula. There's a lot of formulas. This one says the situation now, yeah. F equals to G M and then set type mass over R2. Yeah, okay.
Okay.
Third drawer. There's those stationary satellites that spin around Earth with the centrifugal force, 24-hour circular path, and it's also free fall. Yeah.
Yep.
Yeah, non-geostationary is like shorter or longer than 24 because it's not only around Earth in a circular path. All right.
Okay.
Negligible. Is this the first one? First drawer.
Okay.
Standing next to each other. Or is this like the... Oh, this is like too small, right? I think. Too weak.
Yep.
Too
small compared to the mass of the Earth.
Hmm. It's level very small magnitude. Ah, okay. Masses of energy so small compared to the bodies, resulting from situation. All right. Oh,
Okay.
third law, second drawer. The periods one.
Yep.
KL is more frequent, while people at the US is like less frequent. Relationship between orbital period and the radius. I'm pretty sure if orbital is longer, then it's just gonna radius is gonna be like sure, right? Fair enough, makes sense.
Yeah.
Okay.
So the keyword here is also the orbital period, the T. Okay. So let's watch the video. Let me see, where is it? Yeah, let me put this here. This one. 5 minutes. Let's start now.
Hey, welcome. Today
你听到吗？
啊，听到。
Okay.
we're diving into gravity, that invisible force that literally holds our universe together.
记住要 relate to 那个 drawer 啊，1、2、3、4。Okay.
We're going to connect the dots from a simple falling apple all the way to satellites whizzing over our heads. Let's get into it. So it all kicks off with this classic question. The story goes that Isaac Newton saw an apple fall from a tree and had this massive light bulb moment. He thought, wait a minute, if gravity is pulling that apple down, shouldn't it be pulling the moon down too? Why doesn't the moon just crash right into the Earth? It feels like it should, right? Well, here's the mind-blowing answer. It is. It's the exact same force pulling on both the apple and the moon. The secret isn't in the force, it's all about motion. And once you get that, the whole cosmos just kind of clicks into place. Okay, so our first stop on this journey is with the man himself, Isaac Newton. Back in 1687, he handed us what is basically the master key to understanding the universe, his universal law of gravitation. Newton's big idea is actually built on two really simple concepts that just make sense. First, the more stuff something is made of, its mass, the harder it pulls. So a giant planet is going to pull way harder than a tiny asteroid. Makes sense. Second, distance is like gravity's kryptonite. The farther away things get, the weaker the pull gets, and it weakens fast. Like if you double the distance between two objects, the force drops to just 1/4 of what it was. It's a huge drop-off. And when you put those two ideas together, you get this one beautiful, elegant formula that explains, well, pretty much everything. It's not just about planets and stars. It describes the tiny pull between you and your phone right now. It's the reason they call it the universal law. It's everywhere, connecting everything. So Newton gave us the why, the force behind it all. But, decades before him, another genius named Johannes Kepler had already figured out the how. He laid out the rules of the road for the planets, this amazing cosmic dance. Let's check out his laws. So Kepler's first law was a huge deal back in the day, a real game changer. Everyone thought planets moved in perfect circles. Turns out, nope. They move in ovals or ellipses. And the sun isn't even in the dead center. It's off to the side a bit, at a point we call a focus. And this means a planet's distance to the sun is actually changing all the time. Now this one sounds a little technical, but what it means for the planet is actually really cool. To cover an equal slice of the pie in the same amount of time, when the planet gets closer to the sun, it has to move faster. A lot faster. And then, as it swings farther away, it takes its time and slows right down. So all the planets are constantly speeding up and slowing down on their journey. Okay, this last one looks like some scary math, but the idea behind it is incredibly simple. It's basically a cosmic formula that links how long a planet's year is to how far it is from the sun. All it's saying is that the farther out you go, the longer your year is going to be, and it tells you exactly how much longer. It's the beautiful, predictable clockwork of our solar system. All right, so we've got Newton's law of force and Kepler's rules of motion. So what happens when we humans decide to use this cosmic rulebook for ourselves? Well, we get satellites, our own man-made moons, that we can park pretty much anywhere we want. And this brings us right back to that first question about the moon. Here's the thing. The moon is falling toward Earth all the time, but it's also moving sideways incredibly fast. So as it falls, the Earth's surface curves away right underneath it. If you get that forward speed just right, it falls around the Earth forever. That's what an orbit is. It's basically a constant state of falling, but always missing the ground. And because we know the rules, we can engineer these orbits for all sorts of jobs. You have geostationary satellites that orbit in exactly 24 hours. They stay parked over the same spot, which is perfect for things like TV broadcasts. Then you have non-geostationary ones, which are zipping around much faster, constantly scanning new parts of the globe. That's your GPS, your weather apps, all that good stuff.
So orbiting is one thing. It's like being on a really long leash. But what if you don't want to be on a leash at all? What does it take to not just fall around the Earth, but to snap that leash and break free for good?
This is where we get to a really cool concept called escape velocity. Think of it as the ultimate getaway speed. It's not about how powerful your rocket engine is, it's just about hitting one magic number. If you can get going that fast, gravity's grip just isn't strong enough to pull you back. You're on a one-way trip to the cosmos.
And for planet Earth, that number is 11.2 kilometers per second. Let that sink in. That's over 40,000 kilometers an hour. I mean, that is just ridiculously fast. You could get from New York to LA in less than 7 minutes at that speed. It's truly mind-boggling.
And this one number is so important. It's the hurdle every rocket to Mars or Jupiter has to clear. But even more than that, it's the reason we're alive. The little molecules of air in our atmosphere, they're moving pretty fast, but nowhere near escape velocity. So gravity keeps our precious atmosphere locked in place. In a very real way, this number is the gatekeeper between Earth and the emptiness of space.
So you see, gravity is this incredible paradox, isn't it? It's the force that anchors us, that built our planet, our solar system. But at the same time, it's the one great obstacle we have to overcome to go out and explore that universe. By learning its rules, we learned how to fly. So the only real question left is, where do we go next?
Okay.
OK，明白啊，有新的东西，
嗯哼
我觉得。OK，然后下一个我们是看 podcast。
Welcome to the Deep Dive, the place where we cut through the noise and get straight to the essential physics that governs, well, everything.
From a simple falling object to a rocket, trying to leave our planet for good.
Today we're doing a deep dive into 4 concepts that are just, completely linked. Newton's gravity, Kepler's laws, man-made satellites, and finally, escape velocity.
And we really have to start with Isaac Newton. I mean, the story of the apple is famous.
Right, but the real genius wasn't just seeing the apple fall. It was looking up at the moon and realizing the same force was at work.
Exactly. He connected the terrestrial with the celestial. And his universal law of gravitation from 1687 says that the force, it's directly tied to the masses of the two objects.
So more mass means more pull.
More mass, more pull. But the distance is the real game changer. The force drops off with the square of the distance.
That inverse square law, it explains so much. It's why we feel Earth's gravity so strongly, but don't feel, a gravitational pull from the person standing next to us.
We don't, even though it's there. I mean, the force is so incredibly tiny unless one of the objects has a planetary-sized mass. You just feel the pull of the Earth, not your neighbor.
Okay, so Newton gave us the why. He explained the force. But it was Kepler who described how the actual path planets take.
That's a great way to put it. Kepler's first law, the law of orbits, says planets move in elliptical paths, not perfect circles.
With the sun at one of the focus points of the ellipse.
Right. Though it's funny, for most planets in our solar system, their orbits are so close to being circular that you'd barely notice the difference visually.
But that little difference is key, especially for his second law, the law of areas. Because the speed isn't constant, is it?
Not at all. A planet has to speed up when it gets closer to the sun, and then it slows way down when it's farther away.
So it sweeps out equal areas in equal times.
That's the one. And that flows right into his third law, the law of periods.
Ah, the math one. T squared is proportional to r cubed.
It sounds complicated, but all it really means is the farther out you are, the exponentially longer your year is. I mean, Earth takes 1 year. Saturn, which is much farther out, takes almost 30.
And that very same principle applies to everything we put in orbit today.
It absolutely does. It governs every man-made satellite circling the Earth right now.
Which is a perfect transition. For a satellite to stay in orbit, Earth's gravity is basically yanking on it constantly, providing that centripetal force.
It's constantly falling, but it's also moving sideways so fast that it keeps missing the Earth.
So when we're calculating that speed, how much does the satellite's own mass matter?
That's the amazing part. It doesn't at all.
Really?
The speed it needs, which is v equals the square root of gm over r, it only depends on the mass of the central body. in this case Earth, and how high the orbit is.
So a tiny CubeSat and the massive International Space Station, if they're at the same altitude, they have to travel at the exact same speed.
The exact same speed. Now, where you place them depends on the mission.
Right, you've got geostationary satellites.
Like for communications. They need a 24-hour period, so they hang over the same spot on Earth all day.
And then there are the non-geostationary ones, like for GPS or Earth imaging, that are moving across the sky.
Yep, like the ISS. It has a much shorter orbital period.
Okay, so that's how we stay. But what about how we leave? What does it take to just break free from Earth's gravity entirely?
Now you're talking about escape velocity. It's the minimum speed you need to, in theory, coast all the way to an infinite distance away, so never come back.
And for Earth, that number is huge. It's about 11.2 kilometers per second.
Or over 40,000 kilometers an hour. It is an immense speed. And just like orbital velocity, it has nothing to do with the mass of the rocket you're launching.
Wow. And that high value is actually what keeps us alive, isn't it?
It is. It's so high that the tiny molecules in our atmosphere, which are zipping around at, maybe 500 meters per second, that you can't escape.
So the same physics that makes space travel so difficult and fuel intensive is also what protects our atmosphere.
It's a double-edged sword. And if we can leave you with one final thought on that, just think about Mars.
Okay.
Mars is much smaller, has less mass, and therefore a much lower escape velocity.
Which means it couldn't hold on to its atmosphere?
Exactly. Its atmosphere is about 100 times less dense than Earth's. In the end, the physics of that one number escape velocity determined the fate of an entire planet.
That's a powerful way to look at it, from a falling apple to planetary destiny. For anyone listening, go look up the escape velocities for a gas giant like Jupiter or even our own moon. You'll see just how extreme this universal law can be.
OK，
Alright.
清楚啊。
嗯。
好，我们现在就 go to step number 8。开
The story.
the story 我们都已经讲了那 story。First drawer 就是 Newton Gravity， 他的 story 就是 Shy Gavin， 然后他的女朋友不能太靠近他，因为他很害羞，然后又不能太远哦，太远的话他就觉得他不喜欢他了，他就 heartbroken，所以这个就是那个 gravitational force。然后这个就是我们讲的Earth and Sun get married。Right. Then Kepler's law is the Ong-Apiang. Ong-Apiang is Kepler's first law, second law, third law. O is the orbital. Orbital is representing that there are many girlfriends around him, and they are circulating around him in the orbital format. Then number 2 is area. So the faster heartbeat, if the girlfriend gets near to Ong-Apiang, then the girlfriend will have faster heartbeat. Means the planet, if it is nearer to the sun, then it will have a faster speed compared to when it is further away from the sun. Then the number 3 is the orbital period. So Ong-Apiang sees his girlfriend, KL girlfriend, more frequent every day, but US girlfriend maybe every year. So that is the orbital period. Jeffrey tie up a centipede and spin around. So that is talking about the
stationary satellite.
Yes, centripetal.
And the centripetal force. Yeah.
Yes, centripetal force, which is the gravitational force. And also the Jeffrey is the geostationary satellite. And also we have non-geostationary satellite. So this is the formula. Then the escape velocity is the rocket goes up until it is above the Earth atmosphere where it is in a vacuum. Then they will travel horizontally, and when they're horizontally, it should not be faster than 11.2. If it is faster than 11.2, then you will escape and it will never come back again. Right. So that is the draw number 4, and that's it. How long do we take? 9:19，看一下，就是这个不是在哪里呢？我把这个是这个啊，这个9:19 9:20 AM， 1个小时多一点点罢了，越来越快了我们。
Nice.
Like, okay, let's do this step number It's 9. Let's create a new one. 在哪里啊？这个 T4C3. So T4C3. Okay, ask me 10 MCQ one by one. I mean, upload how? Material.
Loading.
Okay, while waiting for 它 upload，我们看一下这个。这个是我们的 gravitation，然后我们快速的 glance 一下。OK，第二个 drawer Newton Universal Law of Gravitation, right? So what does it talk about? Yeah, so it talk about the Earth and the Sun and the Moon, how they pull each other, and also this formula. It looks very scary at first, but now it looks very friendly now. So these are the calculations. And the relation, gravitational acceleration. This is more focused on the Earth. So we get 9.81. Then this is knowing the value. This is 9.81. Okay. Centripetal force. Drawer 2 already. Okay, anyway. Okay. Now it's drawer 2. This is drawer 2.
This is drawer 3. Is it centripetal force?
Yeah, this is drawer 3. Yeah, you're right. You're right. Yes. So maybe this is the introduction of drawer 3. Okay. And that's it. Then it's drawer 2. The Kepler's law. 1, 2, 3.
Kepler's law.
Yeah, the orbit, area.
Area and the period.
Yeah, you see the area, this one. So when you're here to here, then it's fast. Oh, here to here, then it's faster. When you're here to here, then it's slower. So the area that is covered, this area and this area is the same area. Right, same area. So that's how the Kepler's second law explained. Right, so this is Kepler's third law. You see, there are centripetal force, which is the gravitational force, and there's this we call tangential force, the horizontal force. Only when you have these two forces, then you're always like falling down, but it did not fall down into the Earth, into the sun for this case. If it is satellite and Earth, then it's the same case. Satellite is always like falling down because there's a gravitational force that is pulling you down. But because you also have this tangential velocity, which is 7.7 kilometer per second. So you are like always trying to fall down, but it doesn't fall down into the Earth. Right. So man-made satellite, the formula, escape velocity, and with a lot of calculations, and that's it. So let's go to our MCQ.
Okay.
Let's bring our picture out. Imagine you're in exam and you have your picture drawn out and getting ready to answer the exam questions. Okay, which drawer and which answer?
First drawer, wait, let me read. Newton's gravitation. Oh, this one is the formula. F equals to G, M1, M2. Let's see. And it's only between two bodies. C.
Right.
Gravitational force distance. Do the second row. Yeah. Force distance. Distance. This one is shy Gavin. It's too far. That's the difference. Distance. B.
Yep.
Not centripetal force. This one is the third row. keeps the satellite in orbit. This is the gravitational force. Yeah. Just gravitational acceleration. G m over r squared. Depends on mass. C.
Yep.
First law, second drawer. Hong Piang, many girlfriend. Let's move on. Okay, it's not A. Not the donkey. C.
Yep.
Fastest in orbit. Oh, this one's second, right?
Mm.
The first law. B. Geostationary satellite. This one is the third drawer. Geostationary, not the first one, that one's not. C. It's not escape. Oh, this one is escape velocity. Oh, this one's the fourth drawer. Rocket turns up, turns right at the center. C. Mass of object.
Yep. This formula, right?
The last one. Linear speed of satellite in circular orbit. Oh, it's good. Oh, okay. 9 is A, and then the 10 does not affect the escape velocity of a planet. Is wait, let me read. Radius donkey.
Okay, good. 10 out of 10.
Yay.
Congratulations. Yay. But one thing here is now you need to, because tomorrow is your exam.
Yeah.
So I think what if I'm you, what I would do is, okay, let me stop the video first. Let me stop the video first. Yeah, if I'm you now, tomorrow